Have you ever stopped to think about that uh, invisible dance happening inside your plants? I mean, watering seems simple enough, right? Just add water.
Yeah, you'd think so.
But, in modern soilless growing, getting that water just right, it's way more than simple. It's this delicate, high-stakes balancing act full of hidden forces and some pretty surprising science.
Absolutely. It's really far more intricate than just, wetting the substrate. When
Yeah.
you're managing plants without soil, every single drop counts. And how that water moves, or maybe more importantly, how it doesn't move, that can be the difference between a fantastic crop and, well, a costly failure.
Exactly. And that's why we're here today. Welcome to this deep dive into the really fascinating world of irrigation for soilless plant production. We've got some great source material you shared, and our mission really is to pull out the key insights for you. We want to demystify how water travels through plants and growing media, look at the, frankly, ingenious ways growers deliver it, and explore some of the high-tech methods coming online to boost plant health.
It's about way more than just pouring water, that's for sure.
Definitely. So, where should we start? The basics.
Let's start with the most basic truth. Water is, without a doubt, the plant's lifeblood. But here's a mind bender. A plant's fresh weight might be over 90% water.
Wow, 90%.
Yeah, but less than 1% of all the water it takes in actually becomes part of that fresh mass.
Only 1%. So where does the rest go?
The vast majority, over 99%, is used for cooling. It's released through a process called transpiration. So for growers, it's not just about hydration, it's about managing this complex biological cooling system that's super critical in controlled environments.
Right, temperature control is huge. So this huge flow of water from roots up the plant out into the air, that's the transpiration stream.
Exactly. Think of it as the plant's internal delivery service. It cools, yes, but it's also the transport system. It carries essential nutrients, gases, everything, from the root zone up to every single cell.
Like the plant's grocery delivery.
Pretty much. And here's where it gets really interesting, thinking about how things move. Dissolved elements like nutrients, how do they get to the roots? Diffusion alone, incredibly slow.
How slow?
We're talking hours, maybe even days, for an element to move just 1 centimeter through diffusion.
That's basically useless for a growing plant.
Right. But bulk flow or mass flow, the movement driven by that transpiration stream or by irrigation itself, that can zip nutrients and oxygen right to the root surface in seconds.
Okay, so consistent water movement is the key, not just water sitting there.
Precisely. It's vital for nutrient uptake and keeping those roots healthy.
Makes sense. A plant can't build if the materials aren't getting delivered. So how do plants manage this flow? We know about photosynthesis. CO2 comes in through tiny leaf pores, the stomata.
Yep.
But those same stomata, the doors for CO2, are also the escape hatches for water vapor. That's transpiration, the engine pulling water up. It's this constant trade-off, isn't it? Getting air in versus losing water.
It is. And it's also affected by the microenvironment right around the leaf. There's this thin layer of still air called the boundary layer.
Ah, right.
Air currents thin it out, but water still has to diffuse across it. And if the air is really humid, say over 95% relative humidity.
And water movement slows right down.
Exactly. It struggles to escape. That's why managing humidity is so critical in greenhouses or grow rooms. Too high and transpiration slows, nutrient delivery slows, it all connects.
It sounds like the plant has some control, though. It can open and close those stomata.
Oh, absolutely. Plants are constantly adjusting. They regulate water loss based on conditions, temperature, light, humidity, even wind speed. And of course, the total leaf area of the plant itself influences the potential rate of water loss. It's always trying to find that balance.
Okay, this feels like a good point to bring in water potential. You mentioned these hidden forces.
Yes. This is fundamental. Water doesn't just flow passively. It moves based on energy potentials. Think of it like the effort needed for water to move or for the plant to pull it in. We measure these in kilopascals, kPa, usually as negative numbers.
Negative numbers, okay. And there are different types.
3 main ones we need to understand for soilless growing: matric, osmotic, and gravimetric potential.
Right, let's unpack those. Matric potential first. You called it moisture potential, too.
Yes. It's basically the grip the growing medium has on the water. Think of a sponge, you have to squeeze it to get water out, right?
Yeah.
Matric potential is that force holding the water in the substrate against pressure or suction. And here's the key takeaway for you listening. High tension in a substrate means it's dry. The substrate is holding onto water very tightly.
Making it hard for the plant to drink.
Exactly. And this is a huge difference between soilless media and field soils. Soilless systems need really precise management. We're aiming for a very narrow tension range, maybe 0 to 8 kRa, to avoid any water stress.
0 to 8. That's tight.
It is. For something like stone wool, you might see problems if tension even gets above 5 kPa. Compare that to field soils that can handle a much wider range, maybe up to 75 kPa, and they rarely get below 10 kPa unless they're just soaked.
Wow. So that difference really defines the challenge of soil. You need that precision.
You absolutely do. Then there's gravimetric potential. That's simply just the pull of gravity.
Okay.
It's about 1 kPa for every 10 centimeters of water depth. So in a 10-centimeter pot, the very top of the substrate is already experiencing about 1 kPa of tension just from gravity pulling water down. The top is always a bit drier.
Got it. And the third one, osmotic.
Solute potential, or osmotic potential. This one's all about the dissolved salts, the salinity, what we measure as EC, electrical conductivity.
Oh, the fertilizer called.
Exactly. The more salts dissolved in the water, the lower the solute potential, the lower the water's energy. Water naturally moves from higher energy, like relatively clean irrigation water in the substrate, to lower energy, which is inside the plant roots because they contain solutes.
Okay, like water flowing downhill, energetically speaking.
Right. But if your irrigation water itself is high in salts, that reduces the energy difference. It makes it harder for the plant to pull water in, even if the substrate feels wet. It's like the plant is trying to drink salty water.
Which is much harder work.
Yeah.
So it's this constant balancing act, keeping the substrate wet enough with low enough tension, but also managing the salt levels.
Precisely. And every substrate has its own unique signature curve, or moisture release curve. This shows you the relationship between that tension, the metric potential, and how much water is actually in the substrate.
And that curve tells you important things.
Very important things. It shows you how much water is unavailable, held too tightly for the plant to get, and how much is available. Within that, we look at easily available water, often between 1 and 5 kPa tension, that's where growth is fastest, and then the water buffering capacity, maybe 5 to 10 kPa, which shows how long the plant can last before serious stress hits.
So knowing your substrate's curve is pretty critical for managing irrigation properly.
Absolutely, and here's something subtle but crucial that catches growers out. Even inside one pot, that moisture tension changes a lot with depth. We said gravity makes the top drier.
Right.
But also, as roots pull water out, it can create drier zones. So just looking at the surface or sticking a sensor in one spot, it can give you a totally misleading picture of what's happening across the whole root zone.
That's a major blind spot if you're not thinking about it. Okay, let's zoom in on that root zone itself. It's not uniform, is it?
Not at all. It's heterogeneous. Roots tend to grow downwards. Geotropism and water removal isn't even. You get denser root patches pulling more water, plus evaporation from the surface.
It's patchy. And that affects water movement within the substrate. You mentioned hydraulic conductivity.
Yes, how fast water moves within the root zone. It's generally much, much faster in soilless media than in soil, which is a big advantage.
Yeah.
But we need to focus on unsaturated hydraulic conductivity, UHC. That's how fast water moves sideways when the substrate is moist but not totally saturated.
And why is that specific measure, UHC, so important?
Because if UHC is low, water doesn't spread out well from the dripper. You need a slow drip rate to give it time to move laterally and wet the whole root ball. Otherwise, you get dry pockets.
Ah, okay. So if the UHC is poor, what happens?
That's when you get problems with parts of the root zone drying out, especially where roots are really dense. These areas can become hydrophobic.
Meaning they actually repel water.
Exactly. So re-wetting them becomes incredibly difficult. The weird thing is, the plant might look water stressed, it might be wilting, even if the pot feels heavy because other areas are still wet.
So what can you do in that situation, like an emergency fix?
Well, first, maybe mist the foliage to cool the plant down and reduce transpiration demand. Then you might need multiple short irrigations over a few hours, little pulses of water to try and gently re-wet those hydrophobic zones, reestablish the UHC, and get some oxygen back in there too.
That brings up that oxygen point again. There's this common idea that overwatering automatically means no oxygen, but you're saying it's more nuanced.
It is. It's a really key point, often misunderstood.
Yeah.
Oxygen deficiency usually isn't caused by applying too much water per se, but by stagnant water, water that sits there without moving.
Because the roots and microbes use up the dissolved oxygen.
Precisely. But when you irrigate, The new water flowing in that bulk flow brings fresh dissolved oxygen with it. It can actually flush out the low oxygen water and replenish the supply quickly. So it's often the lack of freshwater movement, the stagnation, that's the real enemy, not necessarily the total volume. Regular, well-draining irrigation is good for oxygen.
That's a huge mental shift for a lot of growers, I bet. Okay, moving beyond the physical movement, let's talk water quality. Especially crucial if you're recirculating water, right?
Absolutely critical. And first glance can be deceiving. Clear water isn't always good water.
Right. You can have tons of dissolved salts, fertilizer, and it still looks perfectly clear.
Exactly. Salty water looks clear. Cloudiness or turbidity, that comes from suspended particles, bits of peat, algae, whatever. You can usually filter those out. But dissolved stuff, that needs different tech, like reverse osmosis membranes if you need to remove it. It's chemistry, not just particles.
And the key chemical metrics growers track are EC, pH, and alkalinity.
Those are the big three. EC, electrical conductivity, tells you the total dissolved salts. We often talk about a nutrient response curve. Too little is deficiency, then you hit the optimal range. Then excess is luxury consumption where the plant takes up more than it needs. And finally, too much leads to toxicity, maybe even death.
So managing EC is about staying in that sweet spot.
It's a constant balancing act in hydroponics. Then there's pH, measuring acidity or basicity. Neutral is 7, but for most soilless crops, you actually want the root zone pH quite a bit lower, usually somewhere between 5.6 and 6.8.
Why lower?
Nutrient availability. Different nutrients are more or less available to the plant at different pH levels. That 5.6 to 6.8 range is generally where most essential nutrients are readily available. Go too low, below 5 maybe, or too high, above 7, and you start running into problems like deficiencies or toxicities.
And what about salt buildup? You mentioned plants take water and leave salts.
Exactly. Plants are very efficient at taking up water, but less so with all the dissolved minerals. So the salts get left behind in the root zone and their concentration increases over time. This can lead to deposits, imbalances, toxicity.
Which is why leaching is important, flushing some water through.
Essential. That leaching fraction, the amount of extra water you apply that drains out, carries away those excess accumulated salts. It's how you manage that buildup.
Got it. And the last one, alkalinity.
Alkalinity is basically the water's buffering capacity against acidity. It's its ability to raise the root zone pH over time as you irrigate. Low alkalinity, maybe below 3 milliequivalents, is usually fine. But high alkalinity, say over 8, that's problematic. It'll constantly push your root zone pH up, so you typically need to treat the water with acid before irrigating.
Okay, that's a lot on the water itself.
Yeah.
So knowing all this, how do growers actually design systems to deliver the right amount efficiently? What are the goals?
The main goal is maximizing water use efficiency, or WUE. Simple concept, hard execution. Deliver water precisely when and where it's needed, absolutely no waste.
Sounds ideal. What limits that?
Well, system capacity is a big one. How many plants can you water at once? That's often limited by your water source, the pump size, the pipe size, the water availability. Large operations often need storage tanks, or they schedule irrigation in zones or circuits, queuing them up to manage the demand.
And uniformity is key too, right? Especially for commercial growers.
Critical. You want all your plants growing at the same rate, hitting market size together. Perfect, absolute uniformity is usually too expensive to achieve, but you aim for the best balance possible. Uneven watering means uneven growth, which complicates harvesting and sales.
How do you even measure uniformity in a practical way?
A common method is just placing collection cups under emitters randomly throughout a zone, running the system for a set time, and measuring how much water is in each cup. Then you calculate a coefficient of uniformity.
And the test duration matters.
Oh, yeah. Pressure can fluctuate as zones turn on and off, so a quick test might not capture the real picture. And it's even harder with subsurface systems, capillary mats, flooded benches.
Why are they harder?
Because you can't easily see or measure the water distribution within the substrate. They rely heavily on being perfectly level to be uniform. And for flooded systems, like ebb and flood, getting rapid and complete drainage after the flood cycle is absolutely vital to prevent waterlogging and oxygen deprivation.
Okay, let's talk delivery hardware. All systems need pressure, obviously.
Right. And a common mistake, often to save money up front, is designing irrigation circuits that are too big, covering too many plants, or using main pipes that are too small.
What problems does that cause?
Big pressure drops, especially at the far end of the line. This means plants near the pump get more water than plants far away. It gets worse on hot, dry days when the demand is highest. Generally, designing smaller, well-engineered circuits gives you much better uniformity and makes more efficient use of your pump.
Makes sense. So the main types of systems, overhead first, sprinklers, booms.
Yeah, overhead systems like sprinklers, booms, even mist or fog, they apply water over the top of the plants. Relatively inexpensive for covering large areas.
Gons.
Quite a few for intensive soilless production. They're often inefficient. A lot of water lands on aisles or walls, not the root zone. They can leave mineral residues on leaves or flowers, which affects marketability. And the big one, wet foliage. Especially if humidity is high or you water late in the day, that wetness is a perfect recipe for diseases.
And mist or fog, they're more for cooling, right?
Yeah. Primarily cooling and raising humidity, yes. They apply very little water to the roots, and they can sometimes fool sensors into thinking things are wetter than they are at the root level.
Okay, what about surface systems? Delivering water right to the substrate.
Right, things like hand watering or drip and microspray systems. They minimize wetting the leaves, hand watering. Well, it's flexible, but its success depends entirely on the skill and consistency of the person doing it. It's often inefficient water channels down the side of the pot, runoff, can lead to very uneven growth.
Drip seems like the precision standard, though.
For surface application, yes. Drip irrigation delivers water slowly, right at the base of each plant. That slow application is key to letting water move laterally through the substrate, wetting the whole root volume. Requires good filtration emitters clog easily, and you need pressure regulators to ensure even flow from every dripper. Installation can be expensive, especially the labor, but the precision and water savings can be huge. You see different types, like thin spaghetti tubes where the length has to be consistent, or emitters built right into the supply line.
And the third category, subsurface systems, watering from below.
Exactly. Capillary mats, troughs, ebb and flood benches, or floors. Water wicks up into the root zone from below via capillary action.
What's the catch there? Sounds efficient.
The main drawback, and it's a significant one, is salt accumulation. As water wicks up and evaporates from the substrate surface, it leaves salts behind, concentrating them in the upper root zone.
Ah, so they need periodic flushing from the top.
They absolutely do. Occasional overhead leaching is necessary to wash those accumulated salts down and out. The other major concern, especially if you recycle the water, is pathogen spread. If one plant gets a root disease, the shared water can spread it rapidly unless you have effective water disinfection in place. Sanitation is paramount with these systems.
Wow, okay. So many choices, each with pros and cons. Now, let's shift to the decision-making, the control side. When do you water and how much? We talk about an irrigation event, a single watering.
Right, and the overall strategy is the irrigation scheme.
The simplest approach seems to be just watering when it looks like it needs it. Occasional irrigation.
Yeah, the as-needed approach. It sounds intuitive, but it's vague. In reality, it often means plants are already experiencing some level of stress and growth has slowed down before they get watered. For maximizing yield and quality, watering as needed is usually watering too late.
So a step up might be pulse irrigation.
Pulse irrigation involves more frequent but shorter watering durations. The idea is to match the substrate's absorption rate more closely. Apply only what it can hold in that short time, save water, reduce runoff.
Sounds good, but you mentioned a risk.
There's a significant risk, especially if the substrate UHC isn't great or roots aren't evenly distributed. If the pulse is too short or the time between pulses too long, those dense root areas we talked about can dry out between pulses. They become hydrophobic, roots can die, diseases can set in. It requires careful management and the right substrate.
And then there's even more frequent watering.
Yeah, high frequency or even continuous irrigation. You see this more in systems with very little or no substrate, like nutrient film technique, NFT, or aeroponics. Irrigation might happen many times a day or be a constant trickle or spray. These rely heavily on that bulk flow concept and need excellent drainage between events to keep oxygen levels up.
So for any automated system, the key decisions are frequency and duration.
Exactly. How often and for how long each time. Frequency is about preventing stress, but also managing humidity. You don't want constantly wet surfaces inviting disease. Smart growers using automated systems also set safety parameters.
Safety parameters, like what?
Things like a maximum duration between events, a fail-safe in case a sensor gets stuck reading wet when it's actually dry, ensuring the plants get watered eventually, and a minimum duration between events, a fail-safe against a sensor getting stuck reading dry, preventing the system from running constantly and flooding everything. Risk management is built in.
That makes sense. And the duration of each watering.
That's dictated by how much water the plant needs to replenish what it used, plus that crucial leaching fraction.
Right, the extra bit to flush salts.
Yep. If your water source is salty or you're feeding heavily, you need a higher leaching fraction, maybe 20–30% or even more sometimes, to keep that root zone chemistry balanced. It's a direct control lever.
Okay, so how do growers decide on that frequency and duration? What's the intelligence behind the decision? The old school method is just looking.
The look and feel method, checking leaf wilt or flagging substrate color changes, lifting pots to judge weight. An experienced grower can get pretty good at it for certain crops, but it's often unreliable. Like we said, visible signs of stress like wilting usually appear after growth has already been negatively impacted. It's often too late for optimal productivity. Really, water stress is more a description of an irrigation failure than a useful management trigger.
It's reactive, not proactive. What about weighing pots? Gravimetric method.
That's better, more quantitative. You track water loss by weight change. But it has issues too. The plant itself is growing, adding weight, which confounds the measurement. And doing it consistently for many plants is labor-intensive. It tends to be used more in research than large-scale commercial settings.
So the most common automated method is just timers, time-based.
Still very common, yes. It's simple, relatively inexpensive. It works reasonably well because most soilless media drain freely, so growers often err on the side of caution and overwater a bit, knowing the excess will drain. It's like an insurance policy.
The downside being
Waste. Wasted water, wasted fertilizer. That's a growing concern environmentally and economically. And if the substrate stays saturated too long, especially during low transpiration periods like cloudy days or night, you can run into oxygen deficiency problems, despite what we said earlier about fresh water bringing oxygen. Consistent saturation is bad.
which leads us to sensors, using tech to get real-time data from the root zone.
Exactly. Sensor-based methods try to measure either the root zone moisture status directly or estimate plant water demand. Tensiometers are a classic example.
They measure the tension, that magmatric potential we talked about.
Precisely. They measure the actual force the plant roots need to exert to pull water out. A big advantage is they aren't affected by salinity, by the EC of the water.
How do they control irrigation?
You set threshold. A high-tension set point, say 5 kPa, triggers the irrigation to turn on. And a low-tension set point, maybe 1 or 2 kPa, tells it to turn off. But they do need maintenance, refilling, and assuring good contact with the substrate. And setting alarms for sensor failure is critical.
Can you override them?
Oh, absolutely. Sometimes, like with very young plants that have small root systems but need frequent nutrient delivery, you might override the tensiometer and irrigate more frequently based on time or under factor, just to ensure they get fed often enough, even if the substrate isn't technically dry by the sensor's measure.
Are there other types of sensors?
Yes, electrical conductance sensors are less expensive, but their readings are affected by salinity, which makes them less precise in hydroponics where fertilizer levels change. They also tend to respond a bit slowly.
And the newer tech?
Dielectric capacitance sensors, things like TDR, time domain reflectometry, or FD, frequency domain sensors, they're becoming much more cost-effective and popular. They measure the volumetric water content directly, how much water is there rather than the tension, and they respond very quickly.
So they measure what's there, while tensiometers measure how hard it is to get.
That's a good way to put it. Both give valuable but different information.
And the cutting edge is model-based irrigation.
Right. This is where you use computers to calculate how much water the crop has likely used based on environmental conditions, and then you irrigate to replace that calculated amount.
How does it calculate that?
It can be simple, like using data from an evaporation pan placed in the greenhouse. Or it can be very complex, using mathematical models like the Penman-Monteith equation. These models integrate data on light, temperature, humidity, wind speed, even the crop's leaf area index to estimate transpiration very accurately.
Sounds powerful,
Well,
but complex.
it requires sensors for the environmental data, a computer to run the calculations, and careful calibration. It can provide highly tailored irrigation schedules, but you still need some grower oversight because the model's assumptions might drift as the crop grows or conditions change unexpectedly.
Wow. Okay, so wrapping this all together,
Yeah.
it's clear that soilless irrigation is this incredibly complex mix of plant science, physics, chemistry, environmental factors, engineering.
It really is. Understanding water potential, managing water quality, choosing the right delivery system, implementing smart control. There's just so much more going on than you might think at first glance. It's both a science and definitely an art.
And finding that optimal approach It really depends on the specific crop, the
Sure.
system you're using, your budget for installation versus labor. It's about balancing all those factors to keep the plants happy and productive.
That's the constant challenge, keeping those plants right in their peak moisture sweet spot without wasting resources or causing other problems.
So where's all this heading? What's the future look like?
Well, we're definitely moving towards even greater precision. True precision agriculture within controlled environments. Think wireless sensors, maybe even sensors integrated into the growing medium. Smart emitters that could potentially adjust flow rates based on real-time measurements of substrate conductivity right at that spot.
Individualized watering for each plant almost.
Potentially, down the line. The goal is to integrate more and more data streams, root zone temperature, actual measured plant transpiration rates, maybe even nutrient levels to anticipate the plant's needs proactively and prevent issues before they start, really tailoring the environment.
It's exciting to think about, but it leads to a kind of provocative thought, doesn't it? You've laid out all this science. We know most of the variables for getting moisture management near perfect. Yet you also mentioned that a huge amount of commercial soilless production still uses relatively simple, often timer-based methods. They rely on forgiving substrates and tolerant plant varieties as a kind of safety net, rather than pushing for true optimization.
That's largely true. There's often a gap between what's known or possible and what's commonly practiced, often due to cost, complexity, or just inertia.
So it means there's this massive potential for improvement still out there. As sensors and control systems get cheaper and easier to use, what does that future of truly optimal plant care look like? When we finally harness all this intelligence to move beyond just good enough watering and get to something truly precise and responsive for every plant, what gains are still on the table?
That's the multi-million-dollar question, isn't it? Better yields, higher quality, less waste, more resilience. The potential is enormous. We're just starting to scratch the surface.